Okay, so we're going to start the third section in this chapter, Systems of Linear Equations. It's reduced row echelon form. It's right here. Let me get rid of this to get more room, and we'll zoom in a little bit. Whoops, that's too much. All right. Now, this section, MVNSE, matrix and vector notation, the idea here is to introduce a notation. We're not really going to do any new math. We're just going to write systems of equations in a more convenient way. If you read this paragraph, the point of the paragraph is that the variables don't really matter in the equation. You can use x1, x2, x3, abc, x, y, z. The equations are the same. In your notation, you want to capture the essential aspects of the equation and not have to write all kinds of extra stuff that's not necessary. Okay, so let's go through and see these new notations. The first new notation is a matrix. Now, you may have seen matrices before. A matrix is basically a square arrangement of numbers. Previously, you've probably seen smaller matrices than this, maybe 2 by 2 matrices. But a matrix can have any number of rows and any number of columns. And the numbers in the matrix are arranged in this rectangular form. Typically, we use m to denote the number of rows and n to denote the number of columns. If I want to denote the entry of b in the second row and the third column, we can write it this way, square brackets b23. We can also just write b23. And sometimes, later on, when we have the matrix be a capital letter, we'll denote the entries of the matrix in small case as b23, for instance. Okay, so test yourself. What would b for 2b? Well, b42 is well, there is no b42, so that does not exist. All right, let's try again. Let's think about b33. What would b33 be equal to? Well, it's third row, third column. It's this number right here. Okay. All right, so let me just say that there are different ways of denoting that. All right. All right, so in the future, when we write equations, we're not going to write the variables. We're just going to write the coefficients of the equations in a matrix form, as you'll see in a moment. Second definition, the definition of a column vector. Now, a column vector is very similar to matrix. It's just a matrix with one column. All right? So a column vector of size m has m rows and one column. For instance, here's an example of a column vector. This column vector has all zeros. We say the entries of this column vector are all 0. If I want to denote the ith entry of this column vector, I'll write it this way. Now, when we did matrices, we had 2 indices for each entry, like we had b23, b33, b42, which didn't exist. But when we have a column vector, there's only one index because we already know there's only one column. So there's no need to worry about saying that it's in the first column. We already know it's in the first column. All right, so how does this relate to systems of equations? Let's take some system of equation. Here's a system of m equations with n unknowns. Notice this goes a11 plus a12, etc. Second equation has A21, A22, etc. Third equation, so on down to the mth equation. See, the first index here indexes the row. The second index indexes the variable, which is also indicated by the column. Look at how this works. A11, x1, A12, x2, blah, 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 A1n, xn. A21, x1, A22, x2, blah, 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 x2n, xn. We can arrange these numbers in columns like this. And the matrix that we obtain from this system of equations is just, well, what you would expect. You take all of these A's in the first column and you put them in the first column of the matrix. So notice that the second index tells you which column the coefficient is in. First index is the row, second index is the column. All right, so we have in this matrix A captured all of the important information on the left-hand side of this system of equations. We've captured all of the coefficients, and we've arranged them in the same way that they're arranged with the variables. Looking at this matrix, I could reconstruct this system of equations, because I know the first column is going to be the first variable, which I can call x1. Second column is the second variable, x2, down to the nth column, which is the nth variable, xn. Okay, so important point here that this system of equations, the left-hand side is associated with a matrix. All right, now what about the right-hand side? Well, here you just have one column. Now this is going to be a column vector. Okay, so that's what we have down here. And because in this system of equations these entries have no variable, we call this the vector of constants. Okay, so we have the matrix of coefficients, which is this matrix A, and the vector of constants. Now, how are we going to write this system of linear equations? Well, let's add one more element to this set of definitions. I also have the variables, and I can arrange these variables in a column. Now you might wonder, why are the variables arranged in a column when here they look like they're in a row? Well, we'll get to that later. But the point is, if I have a set of variables, I can write them in a column like this. And whether I write them in a row or in a column, they're the same variables. And now we have enough notation to represent a system of equations as a matrix with a vector. We write LS of AB. This is a shorthand note expression for this system of linear equations. So this system is LS of AB. Linear system, coefficient matrix A, constant vector B. All right, so for instance, if we have this system, what's the coefficient matrix and what's the constant vector? Well, to find the coefficient matrix, we want to focus on the left-hand side. It's a little bit irregular here. Here's the first row, the first column rather. Here's the second column. Here's the third column. Notice that there's no x3 in this second equation, so that means the coefficient is 0. Here's the fourth column, and here's the fifth column. All right, so this system of equations, if I just look at the coefficients, I read off 2 minus 4 minus 3 plus 5 plus 1. 2, I'm sorry, that's a plus 4. I obscured that. 2, 4, minus 3, 5, 1. You can see that these coefficients correspond to the entries of this matrix. And the vector of constants on the right-hand side corresponds to this vector here. Okay, just a lot simpler. I don't have to write plus signs and minus signs. I just have a very natural arrangement, and you can see that this has the same information that my original system does. Now we're going to do one more thing, is we're going to put the matrix and the vector together. Notice they have the same number of rows. So I could easily write A next to B and we can write that this way. You write the coefficient matrix A, a line, constant vector B. All right. So here's one example. If I have this system of equations, that's right, it's this system of equations, then the coefficient part is the part on the left here, and the constant vector is the part on the right here. You can see that this corresponds to this part, this corresponds to this part. Okay. Now, sometimes we draw a line here, sometimes we don't, but you should understand that in an augmented matrix, the last column corresponds to the vector of constants. Okay, that's it for this section, this subsection rather.